as I was saying, to do integration by parts with definite integrals, the integral that you end up with has the same bounds, and this bit here, the uv, also gets evaluated between a and b. So you can save a little bit of time by evaluating this chunk first before moving on to evaluating this integral. Okay, so once again, we are in the sort of situation where we're using integration by parts to evaluate a single function as opposed to a product of functions. So here at least there's no question about what we should let u be, right? It has to be the arctangent function here. Then we have no choice but to let dv be dx. And now let's fill in the ingredients. So du is the derivative of arctangent. So that is 1 over 1 plus x squared. V is the integral of dv. So in this case, dv is just dx. So the antiderivative of 1 is just x. And now we can plug in the formula. So let's see. U is arctan. V is x minus integral, and this is evaluated between 0 and 1, minus integral v is x, du is 1 over 1 plus x squared dx. Okay. So, if we plug in 1, we get arctan of 1 times 1. If we plug in 0, we get arctan... I'll get it right one of these days. We get arctan of 0 times 0, which of course is just 0, so who cares? Now let's see. So what should we do here? We need to evaluate this second integral. Now, this guy, we can just do a u substitution. If we just let u equal 1 plus x squared, then du is going to be 2x dx. So then this x is going to get canceled out. But before we do that, let's just note that arctan of 1. So let's see, what angle has a tangent of 1, which is also between negative pi over 2 and pi over 2? That's pi over 4. So to find arctan of 1, note that, so by definition, arctan of 1 is going to be y, if and only if tan y is equal to 1, and y is between negative pi over 2 and pi over 2. Right? Just look to the lecture notes on inverse trig functions for this. So what angle between negative pi over 2 and pi over 2 has a tangent of 1? Well, pi over 4. There's only one response. And that may as well be worth remembering, since I feel like arctan 1 is going to come up fairly often in indefinite integrals here, because it's one of the few examples where you can actually evaluate an inverse trig function and get a somewhat nice number out of it. as opposed to some crazy fraction. So this just becomes 0. And then there's all of this. So, as for that integral, like I was saying, let's do a substitution. So use the substitution technique with u equal to 1 plus x squared. Then du dx is equal to 2x. Consequently, dx is equal to 1 over 2x du. So our integral becomes, and let's not lose sight of what we're actually integrating here, pi over 4 minus, oh, and you know what? I always forget to do this. We have to change the bounds as well. So when x is equal to 0, u is going to be 1 plus 0 squared, so that's 1. When x is equal to 1, u is going to be 1 plus 1 squared, so that's 2. Okay, so our new integral goes from 1 to 2. X over, so 1 plus x squared, that is now turned into u, and then instead of dx, we have 1 over 2x du. So this x and this x cancel. We can bring the 1/2 out front. Like so. Okay, so what's the antiderivative of 1 over u? Well, that is natural log of absolute value. And then that has to be evaluated between 1 and 2. So that is natural log of 2 minus natural log of 1. And then finally, we note that the natural log of 1 is just equal to 0, so we can do one final simplification by just making that go away. And if you really want to be pedantic, you can put this into a single fraction. I'm not saying this is necessary, but you know, maybe on a multiple choice homework problem they'll write it like this. I don't know. Anyway. And if you really, really want to be pedantic, you can take this 2 and move it into the logarithm to get to waste a bunch of time typing poorly. So, you know, maybe in the multiple choice you'll see this. And don't be confused, just know that maybe there's some algebraic stuff that you can do to get it into that form. But, I mean, ultimately it doesn't matter. You could always just compare the decimal. You could always just plug stuff into your calculator and compare the decimal answers that you get. Yep. So that's all I have to say about integration by parts for now. I mean, it's a really, really clear-cut procedure. Each individual step in the procedure should be pretty easy, because you're either just taking a derivative or an antiderivative of a simpler function. So yeah, just stay organized and practice with the homework. Yep. The only sort of weirdness, I think, that can be introduced with integration by parts is in this example here, but even then, it's not going to get any weirder than what I've shown here. Yeah. So that's all for now.